In this video, we're going to talk about intermolecular forces, which are different than the intramolecular forces we've talked about to this point. So, intramolecular forces refer to forces that exist within a molecule, such as a covalent bond. Intermolecular forces exist between different molecules, or between ions and molecules, or between different ions. So, let's take a look at these. There are four major categories that we're going to talk about, which include the ion dipole, dipole-dipole, hydrogen bonding, and London dispersion forces. And they all have to do with the polarity of the molecules involved. So first we'll look at the ion dipole, and that is exactly what you would think it is. It's the interaction between an ion and a dipole. Now a dipole is just something with two poles, so a positive pole and a negative pole. So any polar molecule is a dipole. So if we take a look over here, you can see that water's oxygen end is slightly negatively charged, and the hydrogen end is partially positively charged. So when that comes near a sodium ion, which is positive, the water will align itself with the partially negative end facing it, and there'll be an attraction that exists there called an ion-dipole interaction. And when you put salt in water, it breaks apart into the positive sodium cation and the negative chloride anion, and you can see that water surrounds them with the opposite end. So the positive would be attracted to the partially negative end of water, and the negative ion would be attracted to the partially positive end of water. So that's the reason salts dissolve in water. Dipole-dipole interactions occur between two polar molecules. So they can be the same polar molecule, or it can be two different types of polar molecules. In this case, we're just showing the interaction between, say, hydrochloric acid and another hydrochloric acid molecule. So you have a partial negative atom and you have a partially positive atom, and they're going to align themselves so that opposite charges interact. And realistically, we're just showing two molecules here. Really, there's an interaction between all of the molecules nearby in a solution. So they kind of align themselves with some attractive forces existing between the partial positive and partial negative ends. Hydrogen bonding is just a super duper dipole-dipole interaction. So it's the same idea. You have molecules that have a partial positive charge on one end and a partial negative charge on the other. But these ones consist only of hydrogen, which is really low electronegativity, bonded with either a nitrogen, oxygen, or fluorine, which are all highly electronegative, meaning they're going to pull really strongly on electrons, and they have an unshared pair of electrons on that atom. So it makes it for a region with a really high electron density, which is super attractive to partially positive things. So here is just an example of what a hydrogen bond would look like. We have a partially negative, let's say this is fluorine in this case, and this is hydrogen. It would interact with the nearby molecules partially positive hydrogen. So super duper dipole-dipole, that's what hydrogen bonding is. And you can see that in a solution, in a sample of water, that the water molecules would arrange themselves where you have partial negative regions attracted to partial positive region, and that all holds it together really strongly and contributes to a lot of the phenomena we observed about water that we'll talk about in the next video. Now, you can see here some molecules where water we know has very strong hydrogen bonding, and even though it's not as strong of a dipole as hydrofluoric acid, which has a bigger electronegativity difference here between the two things bonded, because there are multiple really weak things, the oxygen really pulls strongly on those electrons and really has a strong net dipole moment. So here you have water with the strongest hydrogen bonding, hydrofluoric acid right here, and ammonia right here. And these three things have relatively high boiling points compared to other molecules of comparable size. For example, methane, which has hydrogen bonded to carbon, so not hydrogen bonding, has a boiling point almost like 160 degrees below water's. Then you can see that as the molecules get larger and become less polar and they don't have hydrogen bonding, that it goes down initially, but then it starts to increase as the molar mass increases. So something's happening here. And what's contributing to this increase when you would expect that it just becomes less polar as you go this way and it would go down? Well, that would be London dispersion forces. So London dispersion forces, they're very temporary, instantaneous dipoles that just result from a temporary lopsidedness of the electron clouds within the atom. So the bigger the electron cloud, the more lopsided it can get, and the stronger the London dispersion forces can get. So if you picture two atoms, when they're completely symmetrical with their electron distribution, you got no interaction. However, if they get lopsided at some point, you end up with a partial negative charge on one end and a partial positive charge on the other, and that can draw electrons from a nearby atom closer to that partial positive charge, thus making a dipole over here. So it's essentially a temporary induced dipole, and while it's not as strong as dipole-dipole interactions or hydrogen bonding, it can have a large impact, particularly as the molar masses of the molecules you're talking about increase. And you can see that right here it shows the boiling points of respective hydrocarbons where the molar mass is increasing, and the boiling point does as well because of the increased ability for the electron cloud to be kind of lopsided. All right, so just a quick summary. London dispersion forces happen in everything, but it's the most important thing when we're talking about nonpolar molecules because while they're not as strong, like I said, they have some impact. If you have a polar molecule, you're going to have dipole-dipole interactions, and that's pretty strong. And then hydrogen bonding is just like a super duper version of that. And then ion dipole is what forms between ions and then polar molecules when you form a solution. So think about what type of interaction you would have with each of these and then answer.